in the last lecture, where we left off was that we had finished proving the sampling theorem. Once you have the samples x of n, you just take those samples and you convert it into an impulse train. And once you have done that, then you effectively, the output of that box, which is xst, you simply low pass filter it. HRJ omega. What you get out is XRJ omega, where this HRJ omega is an ideal reconstruction filter, which is given by T for absolute value of omega less than or equal to omega s over 2. So there is something going in there, which is the sampling period T, and it's 0 otherwise. What we argued was in the sampling theorem that if indeed your input signal that gave rise to these samples, if that input signal was band limited, and what happens is that this omega s, this is greater than or equal to twice the bandwidth, then guaranteed that the signal xrt, which corresponds to the Fourier transform of xrj omega, that is equal to the input signal x of t. That is the essence of sampling theorem, which we proved. This HRJ omega, this is of course the Fourier transform of a filter HRT. And for this ideal reconstruction filter, the Fourier transform of that, the impulse response is simply given by sine pi t over capital T over pi t over capital T, which is simply called the sinc function, sinc of t. So, which means is that xrt, which is the output of our reconstruction, that is simply given by the convolution. Since we have, this is a filter, at the input of the filter we have xst, at the output we have xrt. So the output is simply given by the convolution between the input and the impulse response, HRT. Now, hopefully you remember how we construct this impulse train. That is simply given by summation over n. We just take the samples and we place them at distance of t seconds. So we have this convolution with sinc of t, because HRT is the sinc. And since convolution is the linear operation, we are simply going to take this inside. We have xn delta of t minus nt convolved with sinc of t. And if we again remind ourselves the convolution property that we saw when we convolve a function with an impulse or a delta, the only thing that happens is the function gets moved to the location of the impulse. So we get nxn sinc of t minus nt. And this formula is called sinc interpolation. Effectively, what is happening is that we have these samples that we collected from our original signal. Zero t, 2t, minus t. And at each sample, we are putting a sinc down, which is supposed to pass through these other points. So it passes through the zeros. The zeros of this sinc are at the other sample locations. And this. And similarly, you have a sinc going from here, which passes through all the zeros of the sinc are at all the sampling location. And what is happening is that you just are given a few samples, and by putting sinks at the locations of the sample, then if you add up all of those sinks, where the height of that sink is scaled by the sample value, you get back the function you are guaranteed. It's like you are filling in the values in between. So that's called interpolation, as opposed to extrapolation, when you take samples and try to build up what will happen beyond the samples. So you can play around with this, and there are again many examples that I'm sure you have seen of sinc interpolation. So the main question we want to address right now is what happens if our signal does not come from the class of band-limited signals. Right now, remember, the Shannon-Nyquist sampling theorem is valid only if our signal comes from the class of band-limited signals. If that does not happen, what we want to see is what happens. So what happens if x of t does not belong to the class of band-limited signals? And assuming that we still do the same sampling and reconstruction procedure. We sample the signal every t seconds. At the reconstruction side, we just do sinc interpolation, which means we construct the impulse train and then we low pass filter that. Now, if you remember the last time, we have to begin looking at what happens to xs of t if we have a signal which is either not band limited or it's not band limited to this omega n radians per second. So this xst, this has a Fourier transform which we evaluated last time, which is simply given by a scaling of 1 over t, and you have multiple copies k minus infinity to infinity x of j omega minus k omega s. So up to this point, this equation remains true whether we have band-limited signals or not. But at the reconstruction side, remember what we do is our reconstruction xr j omega, which is the Fourier transform of xrt, that is given by this filter hr j omega 1 over t k minus infinity to infinity x of j omega minus k omega s. And this hr j omega is simply t times this indicator omega for minus omega s by 2 to omega s by 2. This is the notation which says that this function, or this function takes the value 1 if omega belongs to this interval, and it takes the value 0 if it does not belong to this interval. Okay? So this is just a shorthand notation for writing that this thing is 0 everywhere except between minus omega s by 2 and omega s by 2. So we have that 1 over t x of j omega minus k omega s. Our t cancels, and what we are left with is the summation of k x of j omega minus k omega s, and outside of that is this indicator function omega minus omega s by 2 to omega s by 2. Now previously what we saw was that if you are sampling, if you are doing the Shannon-Nyquist sampling using a band limited signal, which means that your omega s is greater than or equal to 2 omega n, then what happens is that this whole thing, there is only one copy, there is only one summation that lies between minus omega s by 2 and omega s by 2. Everything else lies outside that range, and so we only get that xr j omega is x of j omega. Everything else is 0. But if this does not happen, if omega s is less than 2 omega n, then what happens to xr j omega, it really depends upon what is your x j omega. These summations, some of these summations, even beyond the ones for k equal to 0, can survive. So if we just take our example of the triangular function, for example, triangular Fourier transform where we had this, and if we have, if this condition happens, then what we will have are these overlaps. This is our x s j omega, and we are filtering. You can verify that this point is minus omega s by 2, and this point is omega s by 2. So we are filtering this region, and if you filter this region, what you end up getting is a figure like this. Now we saw that last time too. This is just a repetition of that same concept, but now we want to just look at what is happening is that the frequencies that were present here, what happened is effectively these frequencies get folded inside the region where we are doing the low pass filtering. Your original spectrum was like this, and some of these frequencies folded back onto the region where you're into lower frequencies. Essentially, they aliased. They took on a different identity than the frequency that they originally corresponded to. So this process, this is called aliasing. Where effectively frequencies bigger than omega s over 2 fold back into lower frequencies and a significant consequence of that is, of course, that your reconstruction is not equal to the signal that you started with. Now the classical example, in case you can't see this folding happening clearly, the classical example that is given for that is that of a pure sinusoid. So the classical example is take x of t equal to just one sinusoid, cosine of omega naught of t, which of course I can do e to the j omega naught t plus e to the minus j omega naught t over 2. And I can write down its Fourier transform, which is x of j omega. It will be just two impulses at omega naught and at minus omega naught. So I get delta of omega minus omega naught plus delta of omega plus omega naught. It looks like just two impulses at omega naught minus omega naught with areas of pi. So far so good. Now the question is, what happens if we sample this cosine at a rate that does not satisfy the Nyquist criterion? So the condition we will impose is that omega s is bigger than omega naught, which is bigger than omega s over 2. Okay. So because of this condition, we are not satisfying the Nyquist criterion. And we will now try to look at what happens to our reconstruction. So if we look at our reconstruction, if you remember again the formula from previous thing, we have just HR j omega times multiple copies of x j omega. So the x j omega is, we have pi over t, and the multiple copies are delta of omega minus omega naught minus k omega s plus delta of omega plus omega naught minus k omega s. And this HR j omega, I'm just going to replace that with 1, again minus omega s by 2 to omega s by 2. And the t cancels, so I am just left with 1 times pi times the summation and this whole bracket from above. Now, if I look at what I have to figure out is which of these summations really lie in the region minus omega s by 2 to omega s by 2. Those are the only terms that are going to survive. All the other terms are going to be killed. They are going to be multiplied by 0. Now the only terms that survive are the first term is actually delta of omega plus omega delta of omega plus omega naught minus omega s equals delta of, I'm just going to write it a little differently, omega s minus omega naught. Why? Because we assumed that omega s is greater than omega naught is greater than omega s by 2, which implies, so this was our assumption that we don't satisfy the Nyquist criterion, which implies that omega s minus omega naught is less than omega s by 2. So this impulse is going to lie in the region between minus omega s by 2 and omega s by 2. The other term that is going to survive is delta of omega plus omega s minus omega naught. Once again, because of the same reason that since omega s minus omega naught is less than omega s by 2. Okay, so these are the only terms that are going to survive. All the other impulses are all other terms, all other delta of omega minus omega naught minus k omega s for k not equal to 1, and delta of omega, I think I have this error here, this should be simply omega. Omega plus omega naught minus k omega s for k not equal to 1. All these terms lie outside minus omega s by 2 and omega s by 2. So effectively what your h xr j omega is going to look like, it will be pi delta of omega minus omega s minus omega naught plus delta of omega plus omega s minus omega naught. And if I now take its inverse Fourier transform, which is my reconstructed signal, that is simply going to be e to the j omega s minus omega naught plus e to the minus omega s minus omega naught. And what we end up with is that we have simply, our answer will be cosine of omega s minus omega naught of t. So what did we start with? Our x of t was cosine of omega naught t. But once we did the reconstruction, our xr of t is cosine of omega s minus omega naught of t. So the frequency of this thing was omega naught radians per second, but the frequency of the reconstructed thing is omega s minus omega naught. Why? Because this omega naught was bigger than omega s by 2. So what happened was that whatever was the region above omega s by 2, it got folded, and the new frequency became omega s minus omega naught, which is definitely less than omega naught. You can see the same thing pictorially. If you are more comfortable with that, you can draw the multiple copies of these impulses, which is given in an example in your book, and you can do the low pass filter and get the same thing. As an example, if your xt is 8 kilohertz frequency, by the Nyquist criterion, you must sample it at least at 16 kilohertz. So your fs should be at least 16 kilohertz for no aliasing. Now, if I sample this 8 kilohertz, let's say at 12 kilohertz, okay, then I'm going to have aliasing. And the reconstructed sinusoid that I get, instead of that being at 8 kilohertz, that sinusoid will be at what frequency? It will be at fs minus f naught equals to 12 minus 8 kilohertz equal to 4 kilohertz. So the 8 kilohertz frequency that you started with, it will appear as if it was present at 4 kilohertz. That is what aliasing means. Higher frequencies are going to masquerade as lower frequencies. Okay? And in general, if you just input, so here is a typical plot that you see. Let's say that this is your original frequency, which is linearly increasing. So this is going up. This is 0 hertz, and you are increasing in this range. This is original frequency. And if this is your omega s by 2 frequency, this is your omega s frequency, 3 omega s by 2, 4 omega s, and so forth. What happens is that if you sample any frequency, so this is, let me just label it, this is omega s by 2, and between every two lines there is omega s by 2 frequencies difference. So this is, let's say if this was omega s was 8 kilohertz, up to this is 4 kilohertz, this is 8 kilohertz, 12 kilohertz, 16 kilohertz, and so forth. If this is omega s by 2, and you input any frequency up to this, what you recover is exactly the same frequency, because you are satisfying the Nyquist criterion. Your frequency is less than omega s by 2, so you'll recover the same frequency. But if you now have an input frequency which is greater than omega s by 2 but less than omega s, instead of recovering a higher frequency, your frequency will start going down, okay, till it reaches here. Now once it hits 0, at what point it will hit 0? For example, if you are sampling something at 8 kilohertz and you input into the system 8 kilohertz, what you will get out will be 0 hertz. Okay, your new frequency will be 0 hertz. Once it hits 0, and now you still input at higher frequencies, those frequencies will now start appearing as, they will start increasing, and it will keep on doing this kind of zigzag. Your output frequency is never going to go above omega s by 2. Because you are filtering at the output with a low pass filter, your output frequency is never going to be higher than omega s by 2. But how the aliasing happens is that higher frequencies first start falling down. You keep on going from 4 kilohertz to, let's say, 8 kilohertz. Your recovered frequency keeps on going down. Eventually it hits 0. At 8 kilohertz frequency, at 8 kilohertz sampling will give you 0. Now you go to 9 kilohertz, it will start increasing again. 9 kilohertz will appear as 1 kilohertz. 10 kilohertz will appear as 2 kilohertz. 11 kilohertz will appear as 3 kilohertz. 12 kilohertz will appear at 4 kilohertz. It again hits the limit. Now you go from 12 kilohertz to 13 kilohertz, it's going to now start going down again. Okay, so you have, these are your recovered, this is your recovered frequencies. And in sampling, you can never go above that omega s by 2 limit. So this is what happens with the zigzag motion, and that's why when I gave you the cosine example, I not only said that your input frequency is bigger than omega s by 2, I also said that it is smaller than omega s. Otherwise, I will be in a different region. Okay. So let's now figure out what can we do. Aliasing is not good. Why is aliasing not good? Because not only is it that you are not recovering the high frequencies, which is bad enough. You sample 6 kilohertz at 4 kilohertz, you are not going to recover it. That is one problem. But why aliasing is bad is because that same frequency turns up as a different frequency in your system. So not only you don't recover that frequency, you get something that was never present in the signal. So at the very least, what you want to do is avoid this aliasing. If you can't recover that higher frequency, let's not do that, but don't make it appear as something else. So the cause of aliasing is though very simple. Aliasing happens because we assumed that x of t belongs to the space of band limited signal, which is band limited up to omega n hertz. But we input a signal xt that actually does not belong to the band limited class of band limited signals. So the solution for that is, before we sample the signal, what we should do is, first of all, take our input signal and make sure it belongs to the class, the mathematical model that we assumed. We assumed that our signal belongs to the mathematical model of band limited signals. Let's make sure that it belongs to that before we do the sampling. Something which is called anti-aliasing, which many of you have seen, presumably all of you. But the way we are going to drive the anti-aliasing phenomenon is going to be a little bit more rigorous than what you see in undergraduate class. Okay? So what we are going to do is anti-aliasing. What I mean by that is, before sampling x of t, we want to first approximate x of t such that the approximation x, let's call that x tilde of t, belongs to the space of band limited signals. And the way we will do that is, we have this input x of t. What we want to do is some kind of an operation, and we will have to figure out what kind of operation this is. We will approximate this we get out x tilde of t. Now x tilde of t is band limited. So now I can just do the usual sampling. Okay. And of course, if I convert that sampling system, so this is xn, if I convert it back, at the output, now I'm not going to get xt. At the output, what am I going to get? X tilde of t. But we are willing to sacrifice exact recovery of x of t so that at the very least we don't introduce things into our signal that never existed. Okay. The question is, how do we do this approximation? For example, there are many signals that live in the band-limited class. Why should I not just take a zero signal? So there should be some mathematical criterion. And when we are talking about approximation, what we really want is we want to do best approximation. We want to make sure that the x of tilde t that comes out of this box, and we will figure that out what this box should look like, what this x tilde of t, when it comes out, it is as close to x of t as can be possible without sacrificing the condition that it has to belong to the class of band-limited signals. So we are looking for the best signal in the class of band-limited signals. Now, how do we define best? We are going to define best in terms of what we call mean squared error. We are going to measure the error between x of t and x tilde of t, and we'll say we want an x tilde t such that it has the smallest possible error. Okay? So let's write down that error. The way to write down this mean squared error is x of t minus x tilde of t, absolute value squared, minus infinity to infinity, dt. And we want this is as small as possible. Okay? Where the constraint is, of course, you can make this 0 by picking x tilde t to be equal to x of t, right? But that is not possible because the constraint is that x tilde of t has to belong to the class of band-limited signals. So it's not possible to make this 0 unless x of t itself is a band-limited signal. We cannot make it 0. But let's try to figure out what's the smallest possible that we can make it. So for that, we'll have to remember a couple of other properties of the Fourier transform. The first one is, I hope you guys remember, which is called the Parseval's identity. What is that Parseval's identity? It says that if you have a function f of t and its Fourier transform is f of j omega, then the energy in time domain is equal to the energy in the frequency domain. So minus infinity to infinity, f of t absolute value squared dt, this is equal to minus infinity to infinity, f of j omega absolute value squared d omega. This is energy in 1 over 2 pi because we are doing radians per second. This is energy in the time domain, and this is energy in the frequency domain, and the Parseval's identity says that both the energies are equal because you are just doing a transformation of bases, nothing else. Okay. The other property that we need is the linearity property. So if I have x of t minus x tilde of t, let's call that f of t. The Fourier transform of that is, of course, the Fourier transform of the individual summations. So I have f of j omega, which is equal to x of j omega minus x tilde of j omega. I'm using x tilde of j omega to define the Fourier transform of my x tilde of t. So I can then write, because of the Parseval's identity, the error in my signal and its approximation by a band-limited signal, that is equal to the error in the Fourier transform of my signal and the Fourier transform of my band-limited signal squared d omega. Now the next thing is we will break this integration up into two pieces. One piece is going to be for omega bigger than or equal to omega n, and the other piece is going to be for omega between, so omega is between minus omega n and omega n. Standard calculus, I have done nothing special here, just broken the integral into two pieces. Now we will use the key property, which is that x tilde t has to be a band-limited signal. If x tilde t is a band-limited signal, then that means that the Fourier transform of x tilde t becomes 0 after omega greater than or equal to omega n. I guess I'll just do this to make it correct. So now we will use the property of the of our x tilde t, which is that x tilde of j omega equals 0 for all omega greater than or equal to omega n. Why? Because we started with the assumption that x tilde t is band limited. If that is the case, then my error, if I just go from here to here, my error then is simply given by 1 over 2 pi omega greater than or equal to omega n x of j omega squared d omega plus 1 over 2 pi minus omega n to omega n x of j omega minus x tilde j omega squared d omega. So all I have done is just replaced in the first partition of the integration, just replace x tilde j omega equal to 0. Now if we look at this, this term of course does not depend upon the choice of my signal x tilde t at all. I cannot reduce that thing. This term I can reduce. So if I want my error, which was, if you remember, minus infinity to infinity, x of t minus x tilde of t absolute value squared dt, if I want this error to be as small as possible, I must make this second term as small as possible. What's the smallest that I can make this term? I can actually make this 0 by selecting x tilde j omega equal to x of j omega for omega less than or equal to omega n and 0 otherwise. If I select this x tilde j omega, then this x tilde j omega between minus omega n and omega n is exactly the same, and this integral is 0. And I cannot make this integration any smaller. So the best approximation is the inverse Fourier transform of this thing. What is the inverse Fourier transform of this? It is x tilde of t is simply x of t convolved with a filter that gives you this thing. Now, if you now think about back, if you put on back your undergraduate signal processing hat, you know what is this. This is simply x of j omega times indicator function minus omega n to omega n, or effectively you are doing a low pass filtering of x j omega between minus omega n and omega n. Okay, so this filter will be the sinc filter. So what you get is you have 1 over t times sinc of t. Okay. Now, in your undergraduate, you start differently. You say to do anti-aliasing, you just low-pass filter it with an ideal low-pass filter. We have started in a different manner. We have shown that the best thing to do is indeed low-pass filtering this with an ideal low-pass filter. If you do anything else, then you will end up with an x tilde t, which does not reduce the error that much. The filter associated with this filter is called the anti-aliasing filter, HAAJ omega, which is simply 1 for omega less than or equal to omega n. Sometimes you will also see it written as omega s by 2, that if you are defining your band limited class based upon your sampling rate and 0 otherwise. Okay. And your x tilde t is simply given by the output of that. So the way you want to do your filtering is you get your x of t, you pass it through an ideal low pass filter HAAJ omega, which has a cutoff frequency of omega s by 2 if you are focusing on t. You get back x tilde of t, and now you do sampling. The anti-aliasing operation, which indeed guarantees that you are using a signal that is band limited, and then you do sampling. So what have we effectively done here? We started with the mathematical model that we have a band limited signal. And then we said, regardless of what you get at the input for sampling, since our sampling theorem works for band limited signals only, we want to approximate our signal by a band limited signal where the approximation has to be the best possible approximation. This principle goes beyond the band limited signal. If you start with a different signal model, which we will later on, then this principle will stay the same. We will always be doing the same thing. You will say, my signal model is X. Well, if you start with a signal that does not belong to the signal model, you will first find the best approximation of that signal model into that. You will find the best approximation of your input signal into that signal model. And then you will do sampling on that approximation. Okay. So right now, because of the class of band limited signals, it was very easy for us to figure out what the best approximation is. We used Parseval's identity of the Fourier transform. And we did some basic manipulation, and we showed that the best approximation is just do a low-pass filtering. The challenge that becomes is if you are dealing with a signal model, a mathematical model which goes beyond band-limited signals, then what do we mean by best approximation? How do we compute that best approximation? And that is what we want to see by going into a little bit of abstract discussion. And we will show that this Shannon-Nyquist sampling theorem is actually nothing but a special class of sampling strategies. Your signal model is what is known as a subspace signal model. So to do that, we will first write this x tilde t in a special way. And then we will have to cover up some basic mathematical concepts that we haven't seen before, so we'll have to go slowly on those. So instead of writing my x tilde t in this fashion, where x tilde t is just given by convolution with 1 over t sinc t, I'm going to write it in a very special form, and then we'll come back to that form later to relate it to an abstract mathematical concept of approximation by projecting onto a subspace. So what I want to do is write down x tilde t is simply equal to 1 over t. I'm going to expand the convolution. Hopefully everyone remembers the convolution integral. X of tau sinc of t minus tau d tau. Okay. Now when we sample this x tilde t, we get the samples x tilde n. X tilde n is simply x tilde of n t. So if I write it in this convolution integral, I get 1 over t minus infinity to infinity x of tau sinc of nt minus tau d tau. If you look at this, I can also write it as x of tau sinc of tau minus nt d tau. And the reason for that is that sinc is symmetric around 0. So sinc of minus t is the same as sinc of t. So I just take t, I can just change the order. Now, x tilde t is a band-limited signal. We all agree with that. X tilde n are the samples of that band-limited signal. So from the sinc interpolation formula, if we are given a band-limited signal and we are given its samples, we can write that band-limited signal in terms of the summation of all the samples multiplied with shifted sincs. That is the first thing we started with the class, the sinc interpolation formula. So by sinc interpolation formula, since x tilde t belongs to the class of band-limited signals, and assumption is that our t is big enough. Our t has to satisfy, that is the underlying assumption, the Nyquist criterion. We can write x tilde t equals summation n minus infinity to infinity x tilde n sinc of t minus nt. Okay, that's our sinc interpolation formula. Now I'm going to replace the value of x tilde n from above. So what I get is n minus infinity to infinity 1 over t minus infinity to infinity x of tau sinc of tau minus nt. This whole thing is multiplied with sinc of t minus nt. Okay. Now, this 1 over t, I'm going to divide it into square roots. So I'm going to write it as 1 over square root of t and 1 over square root of t. And I'm going to put it into two places. I'm going to say minus infinity to infinity x of tau sinc of tau minus nt over square root of tau. That's square root of t. That's where 1 square root of t will come. And then sinc of t minus nt of square root of t. Okay. And finally, d tau is missing here, and we have d tau missing here. Now, I'm going to say that if we have two functions f of t and g of t dt from minus infinity to infinity, I am going to write them as f and g with these brackets. For those who know, this is the notation for inner product. We will come back to it. Okay. So what I'm going to then do is, and from minus infinity to infinity, I am going to write this as x. I'll keep t here. Sinc of t minus nt over square root of t times sinc of t minus nt over square root of t. What I have done is I have written my x of t. I have written my x of t. The original signal that I started with that I did not really know for sure is band limited. And I have written that in terms of a band limited signal x tilde t by doing some special operation on xt in relation to a sinc and then multiplying them with sinc and taking a summation. Why I have done that? The reason is that once we write it in this form, we will see that this is a special way or a more rigorous way of approximating signals in their signal models according to their signal models. Not all signal models, of course, will work. These are special signal models which are called subspace signal models. And effectively what we will see, if you think about this, this has become our, these are our samples. This is a scalar quantity, right? This integration is a scalar quantity. And then we generalize the notion of sampling beyond sinc. The only thing we will have to do is just replace this in the integration some other function. The general sampling strategy for most models, what it will look like is that someone will give you, you'll start with a signal model. Then someone will give you x of t, and the way you will do the sampling, even you will do a convolution operation here or filtering here. And the filtering may not be as simple as just take a low pass filter. Depending upon what kind of function or what kind of signal model you have, this filtering could be different, but the general sampling strategy will be, for the most of the rest of the class, that you do filtering and then you sample it at nt, t equal to nt. And you will get your samples, which we will call x tilde n. So whenever we end up with a signal model where we will be writing our x tilde t in this summation form, this thing inside the summation, we will always call that as samples. Recovering from the samples will be as easy as taking a similar function and just adding all of those samples times the shifted functions together. Okay. And hopefully things will become clear when we do other kinds of filtering. But right now what I want to argue is that this is what we have done right now has strong connections to the notions of projections onto lines that you might have seen in your undergraduate degrees, or approximations into different bases. Okay. So what we are going to do is move away from the classical view of sampling, which starts with band limited signals and goes all the way forward. And what we are going to do now is we have taken a special case of a sampling, which is band limited signal. We are now going to represent it in a more abstract fashion. And the advantage we will have by doing that is that we can then generalize sampling to a number of cases where band limited sampling may not be the best thing to do. Because as we argued at the start, a model is good to the extent that the signals that we are observing conform to that model. Band limited signal is a good model for some cases, but it may not be good for other cases. Okay. So our goal going forward, we are going to take a break from discussion of band limited signals, and we are going to now generalize some notions that you may have heard about: linear independence, basis, dimensions, but in a more rigorous setting. And then we will come back to this very same equation. So you should probably mark down this equation as a star or something on your notes. We'll come back to this very same equation, and we will say that it's just a special case of a more abstract way of doing projections onto a model, approximations through a model, or sampling through a model. So our goal is going to be that we are going to show that Shannon-Nyquist sampling theorem is just a special case of sampling signals according to a subspace model. And I'm putting subspace in quotes because we really have to define what we mean by these terms. So what we are going to right now do is, we are all familiar with the notion of vectors, Rn, matrices. And what we are going to show is that those notions that we have studied in our linear algebra classes can be extended very easily to more abstract settings. And those abstract settings then help us work with objects like signals as if they were nothing but points in a vector, as if they were just vectors. Okay? And in fact, we end up calling them exactly that, a vector. So our goal in the next lecture or so will be that we will go from vectors in Rn, one-dimensional space, two-dimensional space, plane, so forth, to their abstractions in vector spaces. And again, I'm putting now that word vector space in quotations because even that is something that we have to specify what we mean by that. So let's start off by asking, take the example of a two-dimensional world. You are living in R2. Now, points in R2, we call them vectors. I'm sure all of you have seen that. So this point, let's call it vector V. This vector is given by coordinates V1 and V2. Now, what's so special about this two-dimensional space? What are the kind of things that you can do are the following. In R2, we can do things like add vectors, subtract vectors, in R2, we have something called an origin, which we denote by 0 equal to 0, 0. And the same notions exist in R3, R4, R5, R6, R100. What a vector space is a generalization of the same concepts to mathematical objects that don't, in the traditional sense, will be called vectors. For example, we will end up with a collection of functions, and each function will be called a vector. Now, why do that? If we stay at the notion of vector space, it doesn't help us much. We don't gain anything substantial. But if we keep on adding the things that make, for example, R2 so wonderful, then we will end up with an understanding that signals can be thought of as living in a space which has geometry. We have angles, we have lengths of vectors, and things like that. Okay? But all of those concepts need to be formally developed. Some of them will develop more rigorously, some others we will sort of brush upon and won't be so rigorous. So I think we won't be able to finish the formal definition of vector space. I'll just say the following. A vector space, it's a generalization of these nice operations that we can do in n-dimensional Euclidean spaces to abstract mathematical objects. And there is a formal definition of a vector space. If any collection satisfies those properties, we say that is a vector space. An example of that, if you want to talk crudely, how do you define a paper? If you collect different kinds of papers on which all of the students are writing in this class, they are probably going to look different in color, in their size, in how they have ruling, what kind of rule they are using. But at the end of the day, if you are only concerned with writing something, someone may prefer one paper over the other, but the general notion of what a paper means stays the same for all of us. It's the same when we define abstract mathematical concepts. A vector space is a general concept. It doesn't have to be R2 or R3 or R infinity, anything that satisfies certain concepts. A paper is a paper. If you can write on it, for you, that might be a paper. So someone can give a very rigorous definition that if something which is made up of perhaps wood pulp satisfies these properties, we all agree we will call it a paper. Now we don't do that in our non-mathematical world, but that is what abstract mathematical concepts are. We all agree that if something satisfies certain properties, then we will end up calling it X, Y, or Z. And vector space is something like that. A collection of objects can be, you can say the collection is a collection of houses or collection of people. As long as the collection satisfies certain properties, you can do certain operations on those objects. You can add things. There is something called a zero. Then you have a vector space. We'll go through the formal definition in the next class, and we will build through that and argue that the space of band-limited signals is nothing but actually a subspace in a vector space.